Okay, welcome everyone to the last Mind and Z lecture for this program. Yeah, good job everyone for for sticking it through. Right, we got all three people who made it to the very end. Um, so today, if everyone got the slides, I um I really put a lot of effort into making these last night. As you can see on it, I guess I'll share my screen. Um, it says today we'll go over some problems, right? Just practice the skills, the techniques that we've learned over the past few lessons, right? And yeah, we'll just go over some BMO1, NZMO, and AMO problems. So that's the round one of the British Maths Olympiad, obviously the New Zealand Maths Olympiad, and then the Australian Maths Olympiad. Okay, so let's start with some BMO1 problems. Um, and you can just find these on like the British Maths Olympiad like website or the UK Maths Trust website. You can just go search up BMO1 problems. They're all here. I would probably recommend like doing problems after like say 2005, somewhere around there, because the old ones, they're a bit weird sometimes. And you can just click on like any random paper. Okay, I don't know. I'll click on 2009, and you know, you can just do any of these problems. I guess we'll probably just look at problems, like from in the range of like problems 1 to 3, because like maybe 4, 5, 6 are a bit harder. So okay, let's have a look at this problem here. Isaac attempts all 6 questions on an Olympiad paper in order. Each question is marked on a scale from 0 to 10. He never scores more in a later question than in any earlier question. How many different possible sequences of 6 marks can be achieved? Can he achieve? Actually, this is a pretty interesting question. It's uh, I'm not sure we necessarily taught the I mean there's definitely like a smart way of doing this, right? There's like a quote unquote like a kind of like a magic solution. Um I'm not sure we necessarily taught that technique, but I can teach it now, I guess, right? So maybe I'll let you guys think about this for like 2 minutes, and then I'll give you guys a bit of a pointer. I'll pull up a whiteboard, whatever, like sharing function, yeah. Just because Google Jamboard's like gone now or something. Okay, I'll send a link to the whiteboard in the chat. Okay, so does anyone have any ideas on, maybe how to get started on this problem? Yeah, okay. If you don't, that's okay. I think this problem's a little bit tricky. Um, I mean, one way you can approach it is just by doing like a bunch of cases, which is it's not ideal, and it's quite bashy and it's long. I think it does get you there in the end. And if you're struggling in the exam and you really don't know what else to do, then I mean, you have they give you what, 3.5 hours for the exam paper. Yeah, maybe you could just list out like a bunch of cases and then just do a bunch of just a bunch of like work, right? And if you do it all correctly, I'm sure you get the correct answer at the end. I'll give a hint towards like maybe the cleaner solution, right? So like the trick is visualizing I guess the marks using a table. So okay, I'll draw what I mean here. So if you imagine you have each of these, okay, wait, if you zoom out a bit. So each of these grid squares, one, two, three, four, five. One, okay. Let's draw a 6 by 10 table. Yeah. One, two, three, four, five, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Um, Something like this, right? Where these are like, you know, where the x-axis here for the graph represents the 6 questions, and then maybe these lines represent how many marks you got on the question, right? So if it's completely like all the way at the bottom, that's 0 marks. And if it's like filled all the way, that's like 10 marks. And maybe I'll color it in red, right? So maybe you get 10 marks on the first question. So look something like that. If I kind of draw it's like a bar chart, right? Maybe you get 10 marks here. Maybe you get 7 marks in the second question. Okay, maybe you get 7 marks again on the third question, right? Because you never get more on a later question than any earlier question. So I can't, go up on the next question. You can only stay at the same level. We can go down. Um, okay. And then maybe something like this. He gets 0 marks on the last question because he doesn't attempt it at all. Um, so you can kind of like visualize what it means to um achieve 6 scores of like kind of like non-increasing order from 0 to 10 using a um chart like this. And actually, it's pretty useful if what we do is well, that thing just raises everything. That's not great. But if you if you kind of delete if you just leave the portion where you just have well like the necessary information, right? If you Okay, I'll just delete this. Sorry. Oops, that was a lot of things that got deleted. But if you just draw like the caps, like the tops of of the bars for the graph, you can kind of visualize it something like this, right? 7, 7, like question 4 you get 5, question 5 maybe you scored 4, and then question 6 you scored 0, right? Something like this. Um, okay, I guess I won't finish the solution now, right? But maybe if you visualize every single like possible combination of scores, right? Possible sequence of 6 marks, you can think of it as a bunch of like horizontal lines um spread out across this like 6 by 10 grid. And you're trying to count how many uh like how many ways there are of, putting these six horizontal like like caps, right? So you have these six lines, one, two, three, four, five, and six. And we're trying to see how many ways there are of putting these six such that they never go up, right? Like they're always going down or staying at the same level as you go from each question to the next successive question. And I guess it's still not obvious how you like would be able to count these, right? The silence, by the way, is me giving you guys a bit of time to think about it. Um, okay. Anyone have any ideas? No, okay, that's cool if you don't. I think the reason maybe it's kind of hard to count this is it feels a bit disconnected, right? Like you just have these like floating like lines in the middle of nowhere. Um, so actually what you can do is if you connect the ends of these lines with vertical lines, right? Where you connect where one line ends and where one horizontal line starts with a vertical line like this, then actually everything becomes connected and you now instead of having some floating, horizontal lines, you have everything being connected and you have a path. Specifically, you have a path from the top left to the bottom right of the script, right? And in fact, any path you draw that strictly goes down and to the right, see, like any random path you draw is just a legal set of like marks, right? Because you just look at where the horizontal lines are. So this path that I just randomly drew is equivalent to getting 8 marks in problem one, 8 marks in problem two, 8 marks problem three, 7 marks problem four, 3 marks in problem five, and 2 marks in problem six. So actually, the possible number of sequences of exam marks that he can have is the same as the number of paths there are from the top left to the bottom right that only um like move down and to the right, never going up or to the left, right? So it's like, like another example is something like this. Right. Um, well, okay, maybe I'll just draw one more, right? Okay, this time he did much better. He scored, 10, 10, 10, 10, 8, and then 6. Um, so we turned this problem from, like a counting problem about like a sequence into one about paths on like a 2D grid. I think that's one technique that I think we were maybe gonna make a lesson on it, but never did. Sometimes it's very useful to visualize things in 2D with like a table or a graph or a grid, because that can reveal more information about the problem, right? When you structure it and like in 2 dimensions. And so now Okay, I mean this problem itself isn't very easy, right? How many paths are there from the top left to the bottom right? Um, I'm trying to think. Did we ever cover this in a previous tutorial? Um, I think we did. Did we? It might have been in the Trojan tutorial. I'm not sure. But anyway, this is like a pretty famous problem or a pretty well-known problem. It's, in an n by n grid, how many paths are there from, one corner to the diagonally opposite corner? Where you're only allowed to move like, you know, well, in this case, down and to the right. Um, I think it's good to just like maybe know the solution to this or like just recognize it because it is, I mean, it's pretty common and the idea is pretty common, right? So, okay, I think we've kind of gone past the main idea of this problem, right? Like the main point of this problem, or the key idea, the key insight is turning the visualizing the problem, visualizing the information in the problem using a grid, right? So now that we've used this grid, used this table to visualize it, and we've reduced the problem to this kind of more well-known problem of how many paths are there from the top left to the bottom right, I'll just quickly present the solution for how you would figure this out. Okay, so as we're moving from the top left to the bottom right, we can make two types of moves. The two types of moves we can make is we can make a right move, right? Going right, or we can make a down move, which I'll denote by D, going down, right? So first we make a right, like in this path, for example, we make a right move, then we make a down move, then a down move, then a right move, then a right move, then a down move, then down, down, right, down, right, down, 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 right. And how many like and if we look at this as a sequence of rights and downs, then this path can be kind of like given an ID, right? An identifying sequence. I mean, this path is just right, down, down, right, right, down, down, da, 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 right? And you just write down all the rights and downs. And if you gave the sequence to a computer or to a person, they'd be able to reconstruct the path by following exactly the sequence, right? Right, down, 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 right, right, down, down, right, down, right, down, 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 right. So how do we make sure that this path, I mean, in particular, like what are some properties of the sequence? The two like key parameters is the number of rights and the number of downs. Because this is a 6 by 10 grid, right? 6 by 10 grid, we have exactly 6 rights, 6 R's, and 10 D's, right? You have 1, 2, 3, 4, 5, 6 rights, and then you have, one, okay, maybe, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, 10. Okay, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 downs. And yeah, you have 6 rights, 6 R's and 10 D's because you have to move 6 times to the right and you have to move 10 times down to get from the top left to the bottom right. So our path here is just a sequence of 6 R's and 10 D's jumbled up, right? That is a sequence. And in fact, any sequence of 6 R's and 10 D's jumbled up make a path, right? Like if I just randomly write down a sequence of 6 R's and 10 D's, um, you know, here I'll have, yellow path, right? R, R, D, 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 R, D, D, R. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. If I just write down a sequence of 6 R's and 10 D's and I follow it, right, right, down, 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 right, down, down, right, down, 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 right, down, right. I don't think I followed it correctly. Oh, I should have gone one more down here. Oops. Sorry. Right, right. One, two, three, four. Right. Down, down. Right. Down, down, down. Right, down. Right. Yep. Okay. So I just made a new path there. So we've transformed this, problem, which is about finding the number of paths, into a problem which is now finding the number of sequences, right, of 6 Rs and 10 Ds. And I think that's a lot more manageable, right? That's something that maybe you learn as like basic counting and combinatorics, right? How many ways are there of arranging 6 Rs and 10 Ds in a line? Um, and maybe, I mean, okay, now I'll ask, does anyone like have a way of solving this, like simplified problem? Oops, that's yellow. Um, okay, no, no one's answering. I think it's good. I think it's good to know how to do this by yourself, right? So maybe I'll start with some simple examples. Well, okay, let me ask some like simpler examples, right? How many ways are there of like arranging A, B, C, D in a row? And what I mean by rearranging the letters A, B, C, D is maybe something like A, B, C, D would be different from, B, C, A, D is different from C, B, D, A. Um, okay. You know what? I'm not sure if okay, I guess people don't really want to speak. That's fine. I'll just quickly go over this as a quick refresher. And hope you guys, either know from somewhere or, maybe past my Ninja tutorial or maybe from school or maybe just from your own reading. Um, but anyway, the answer for this question is because there's four letters, the answer is 4 factorial, which is defined as, product of all the positive integers less than or equal to 4. So 4 times 3 times 2 times 1, which is 24. And the reason the answer to this is there are four, choices for the first letter. Afterwards, there's 3 choices for the next letter, then 2 choices, then 1 choice, right? So multiplying all the choices together, you have 4 times 3 times 3 times 1. There's 4 factorial is 24. So the answer for this one's 24. But what happens if how many ways are there of rearranging letters? Let's say, if I change A, B, C, D to A, A, B, C. Well, you can still do the same thing where you're saying there's 4 choices for the first letter, then 3 choices, and 2 choices, and 1 choice. But if we denote these A's as A1 and A2, so we give them different identities, they're different A's now, then our counting would count A1, A2, B, C as a different combination from B2, B1, BC, which is not good because if we get rid of the subscript 1 and 2, since they were never there to begin with, then actually we find that these should be the same sequence because we shouldn't be differentiate between the first A or the second A. They're like technically identical, right? So we overcount by a factor of 2. We count too much by a factor of 2 because we count every combination or every permutation as 2 separate permutations when it's really 1. So the answer for this one is you get your 4 factorial as before, but you have to divide it by 2 factorial now, where 2 factorial is the number of ways of arranging this. So if you had something like, what's the number of ways of rearranging the letters A, 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 B, C? If these are all distinct, the answer will be 5 factorial, but you have to divide by a factor by which you overcount. In this case, it's 3 factorial because because there's 3 factorial ways of like arranging these 3 A's, right? If we give them subscripts A1, A2, and A3, there's 3 factorial ways of permuting A1, A2, and A3. Right. So there's 6 ways to permute these, all of which are counted as distinct under our 5 factorial count here. Actually, sorry, if we're being, more strict, it's 3 factorial ways of permuting. Where 3 factorial just equals 6, right? There's 3 factorial ways of permuting. Therefore, we overcount by a factor of 3 factorial. Therefore, we need to divide our final answer by 3 factorial. Okay, so if we complicate this just a little bit, if you follow the same logic through, and then I ask you for, oops, I just deleted my entire question now. I didn't know you could do that. Okay, sorry. Yeah. If I ask you the same question about maybe something like how many ways are there of rearranging the letters? Maybe, you know, A, B, B, A, B, B. You do the same thing, 4 factorial, but now since there's 2 A's and 2 B's, you would divide by 2 factorial and 2 factorial. So that's like a general way of like I don't know, maybe you knew it, maybe you didn't know it. If you didn't know it, maybe this was a bit too quick, sorry. But hopefully, that was just a good reminder. Um you divide by, 2 factorial here and 2 factorial here for the 2 A's and the 2 B's. So for our thing where we have six D's and sorry, 6 R's and 10 D's, that's 16 letters in total. So you would maybe say it's 16 factorial and you divide by the factor by which you overcount, which is 6 factorial times 10 factorial. And actually what you might notice is that this is the exact formula for 16 choose 10, or and by like binomial coefficient node or whatever, right? 16 choose 10, right? And if you know what this means, it's the same as the number of ways of choosing 10 objects from a set of 16 objects. And the reason these two are equivalent is another way of thinking about how many ways there are of arranging 6Rs and 10Ds is start by having 16 blank squares 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 blank spots. And I'm going to say I'll place 6Rs in some of these spots, right? I'll randomly place 6Rs, and the remaining spots, um, and the remaining spots I'll fill out as these. So the problem is equivalent to choosing 6 of these 16 spots to put 6Rs. Um, so you can also say the answer is 16 choose 6, right? Which is the same as 16 choose 10. Because choosing 6 is the same as choosing 10, right? Or choosing 6 spots from a list of 16 is the same as not choosing 10 spots from a list of 16, i.e. leaving 10 spots blank. Um, did I just delete everything? Okay, well anyway, I think I just deleted everything I just wrote, which is fine, I guess, as we were nearing the end of the problem. Anyway, so we figured out the answer was 6 choose 6, which is equivalent to 16, sorry, 16 choose 6, which is sorry. Oh, okay. Well now everything's back again. Well, that's great. Okay, thanks. So 16 choose 10, which is equivalent to 16 choose 6, which is equivalent to 16 factorial divided by 6 factorial times 10 factorial. Um, so anyway, this is the answer, but by various methods, right? Either choosing 6 blank spots from a list of 16 blank spots, or multiplying or finding the total number of ways of rearranging 16 arbitrary letters and then dividing by how much we've overcounted. Um, yeah. So if you know about the formula for like the choose function or binomial coefficients, this is what you get, right? 16 factorial over 10 factorial times 6 factorial. Yeah, so each of these, and I can't compute this, is a pretty large number, but each of these like combinations is a unique string of 6Rs and 10Ds, which then corresponds to a unique path going down this graph, which then corresponds to a unique um like sequence of exam scores for Isaac. So yeah, by going through, it's kind of like, I mean, it's kind of complicated, kind of not, right? Pathway where you turn, you kind of do this series of steps where you simplify the problem every time, right? And eventually, you get this pretty nice clean answer of just 16 choose 6. Um, yeah, cool. That's great. I guess the key takeaway here, I mean, the key takeaway, I guess, is the key trick of the problem is turning it into a graph, but also I think it shows sometimes how it's important to just kind of simplify the problem one step at a time, right? First, we'll simplify it by, turning it into this graph-like problem, grid-like problem, and then we'll simplify it by turning it into this sequence-like problem, and then we'll, whatever, and then eventually you get the answer. Um, okay, cool. I guess we can move on to next year, 2011. Let's see if there's any comedy problem here. Um, hmm. Okay, problem 4 looks kind of interesting. Maybe should we try it? Um, yeah, I guess we can try problem 4. So we have m balls in one bag and n in the other, where m and n are positive integers. And we have two different moves we could do. So one move we do is remove an equal number of balls from each bag. And the other thing we can do is double the number of balls in one bag. Okay, let's answer the first question. Is it always possible to empty both bags after a finite sequence of moves? And I think, okay, sorry. Sorry. And whenever you have a problem like this, right, it's always good, right? You have, a game, a kind of thing where you have a sequence of moves and you have, a thing you're trying to, like an end goal you're trying to achieve. It's always good to just, maybe play around with the problem yourself, start with your own balls, and and see if you can actually, achieve the goal. So, okay, I mean, I have a vague idea for what I think the answer is, but I don't necessarily know the proof yet. So we can kind of go through this together, right? Okay, I'll start my problem here. So let's start with you know, m equals 5. I'll use blue. I don't know why. Let's start with m equals 5 and n equals 3. Oh, okay, and I'm go. Thanks, whiteboard. Okay, you know what? I can't do it on the whiteboard, so I'll get you guys to do it yourself. Um, th Start with 5 balls in one bag, 3 balls in the other, and see if you can empty both bags using the two operations that we have. I'll try with you guys. So whiteboard back. Yes, our whiteboard's back. Woohoo. Okay. So yeah, did anyone manage to win? Um, I'll give a hint. I mean, it is possible to win, right? You can find a sequence of moves. With the starting number of balls, 5 and 3, using these two operations. So only these two, right? We're not looking at operation B dash right now, right? Remove an equal number of balls from both bags and double the number of balls in one bag. It is possible to empty both bags after final sequence of operations. Um, like maybe keep looking if you haven't already. If you have, you can like like privately message it to me or something, just to, like tell me that you found it. Okay, you don't have to message me the series of moves. You could just say yes if you found a sequence of moves, right? Just let me know. And if you like haven't if no one here like can find the move, I'm not necessarily sure I want to continue with the solution just because I feel like there might be a fundamental like misunderstanding of how the problem works. Yeah, you know what? It's fine. I'll give you guys like 5 more minutes just to try to figure it out. And yeah, if you figured it out, right, just type like a yes or something into the chat. Um, yeah, does everyone here like understand the question? Just checking, just making sure that everyone's on the same page here. Okay, sorry. Let me take it one step back. It's like, is everyone here? Am I talking to someone? Hello. Okay, you know what? My bad. I'm talking to the people on YouTube now. Apparently, right? Sorry, guys. Um, yeah. I guess if you're watching the recording, this presentation is for you. So hopefully you've had enough time now to have a think about the problem, and I'll get ahead with this. Go ahead with the solution. So if we have five balls in one bag and three balls in the other bag, I'll denote them as five and three here. We can do a series of operations, like randomly, and like a lot of things work, right? A lot of things work. So maybe one idea we can try is we kind of want the numbers to be of similar magnitude, right? Because we're eventually trying to reduce them down both to zero. The only way to reduce them both to zero is to have them equal the same number, upon which we can apply operation one and take them both down to zero. So maybe I'm gonna do operation two on number three here and multiply it by two to get five and six. So now five and six are pretty similar. Right? Maybe I can minus four from both to get them, to one and two. Notice that I never want to remove all of a number before two numbers are equal. For example, for five and six, I never want to take it down to zero because then I'm left with zero and one, and I'm never going to be able to increase this number more than this, right? Because zero times two will always stay zero. So this number is always going to be less than or equal to zero. But this number, um, yeah, like if I have something like we have zero and a positive integer, I'm never going to be able to get them to be the same integer, right? The same number. Because I can remove the same from both of them, which will make this negative, or I can multiply this one by two, which makes the difference bigger, or I can multiply this one by two, which either doesn't change the difference or makes the difference bigger. In every case, the difference between the two numbers will always like will never decrease. So I'm kind of screwed if I ever make one of the numbers zero without making the other one zero as well. So since I don't want to make it zero, maybe I'll just make it one, right? I'll minus four from both. And then I will have something like one and two. And from here, maybe it's pretty easy to see how we get these to be the same number. I would just multiply this one by two. So okay, I'll do times two here, minus from four from both sides here, times two for this one, right? I'll do a different color, I guess. Um, times two, minus four, times two. Um, so I have two and two now. And finally, I can minus two from both, and I'm left with zero and zero. So that's cool. I managed to do it for five and three, right? And if you try it with a bunch of other like combinations of numbers, which is something you should do, right? You want to figure out, is it true first before you try too hard to prove it. Um, you should start to notice that yeah, it is always possible, right? It does seem to always be possible. Um, somehow you minus some number from both of them, then you like multiply the smaller one by two a couple times, then you minus the same number from both of them again, then you keep doing this process. Eventually, it feels like the two numbers get closer and closer together until they become the same number, from which you can multiply them, or you can minus them both down to zero. Okay, so whenever you have a problem like this, where you think the answer is yes, I can always reach my end goal, you want to provide some kind of algorithm or some kind of method for which you can follow, for which you can always complete the goal for any two starting numbers. So we don't really have like a well-defined algorithm right now, right? I mean, maybe like a general heuristic is I want to get them as close as possible. So I want to try maybe make some algorithm that minimizes the difference between the two numbers. Cool. Um, how can we do that? The other thing you want for an algorithm is you want repeatability. Like you kind of want something that you can do for any two pairs of or any pair of two numbers, right? Um, like this example isn't so good. The reason we multiplied by two at the start is because three times two is six. It's kind of close to five, right? But that's not going to necessarily hold for any two pairs of numbers, right? Like if I start with something like seven and like 12, multiplying by two will get me kind of close, but it won't get me the same closeness as my first example, right? So I can't say for my algorithm to always multiply by two in the first step because that's not going to work for every pair of two numbers. So maybe let's try something um like a bit different, right? Like maybe if you play around with enough numbers, um like one thing that is like maybe if I have some two really large numbers, okay, for example, if I have 100 on one side and 37 as my other number, so um like an issue here could be like of how like 37 is a bit too big, right? Of how like quote unquote volatile it is. And what I mean by that is that when I multiply by two, well, if I multiply by two, I get 74, which is quite far from 100, a little far from 100, right? It's still like 26 away from 100, which is fine, but it's like not great. And if I try multiplying by this by two again, now I get 148, which is even worse, right? Now it's 48 away from 100. And the reason it's like bad like this, the reason like it's always going to be like so far from 100 is because 37 is inherently just kind of a large number, right? So every time you multiply by two, you're going to increase like its value by a lot. And when you're increasing its value by a lot, you can't really get that preciseness that you want. You kind of want to be able to tweak its value more precisely than just multiplying by like multiples of 37 every time. So maybe what like this kind of leads us to thinking something we can do is, hey, let's make this number a little less big, right? 37 is a bit too big, but we have an operation we can do to make it smaller. Let's subtract 36 from both sides. So now we have um, a very nice small one on the right side. And we still have a somewhat decently big 64. And oh, okay, my example here was a bit nice because now you have 1 and 64. You can obviously just multiply this one by two like six times and you just finish. But okay, maybe let's change my initial example to something like 110 just to make it a little bit less easy for us. So if you multiply 36 from 110, you get instead of 64, you get 74 now. Actually, sorry, to to demonstrate my argument a bit nicer, I will I'll make it 90. So you have 54 now. Okay, cool. So let's multiply this one, right? Let's multiply this one um until we get a number bigger than 54. So let's multiply it by one twice. That's two, that's four, that's eight, 16, 32, 64. So we multiply by two six times and we end up with 64 and 54. Cool. And now, right, now we can minus well we can subtract until the smaller one becomes one again. So if we do this, we get 53 minus 53 on both sides, and we end up with 1 and 11. Okay, and like notice that every time we're doing this, it kind of feels like the numbers are getting closer and closer. Well, sorry, not sorry. Let me just repeat this one more time. Right? Well, I'll multiply this one until it gets to a number bigger than 11. So 2, 4, 8, 16. I multiply by 2 4 times, and I end up with 16. Here I end up with 11. If I multiply 11 from both sides, or sorry, if I multiply 10 from both sides, keeping the smaller number to 1, then now I have 6 and 1. And so we started with 90 and 37. Then we got to 50, then we got to 1 and 11. Well, so we from 1 to 54 to 1 to 11 to 1 to 6, we see that like they're getting closer and closer together, right? We started with a difference of 43, then we moved to a difference of 10. Now we're at a difference of 5. And let's see what happens if we, keep on repeating this process, right? We multiply this 1 until it's larger than the 6. We have 8 and 6. Okay. We see now that the difference is 2. So it's even better. 1 and 3. And now we see that our difference is 1. And finally, we'll see that our difference is 0. And once our difference is 0, obviously you can just subtract this number, right, from both sides, and you get 0 on both sides. And cool. That's that. Right, that's done. Right. So let's take a quick recap of what we've actually done, right? We start with two numbers and we minus from both numbers, we subtract from both numbers, such that the smaller one, in this case, 37, becomes 1, right? So we minus 36 from both sides. Then we'll multiply that 1 by 2. So we'll multiply by a power of 2 until it becomes larger than the other number. And we repeat this process. We subtract from the smaller, well, we subtract until the smaller number becomes 1. Then we multiply until it becomes bigger. Then we keep doing this. And eventually it looks like our difference gets smaller and smaller. So we've provided an example of an algorithm here, and it remains to show that this algorithm works. In other words, for whatever two starting numbers we start with, if we apply this algorithm, we're going to eventually end up with two numbers that are the same. One way we can view this is by considering the difference of the two numbers and showing that this difference is a monovariant, well, a strict monovariant that always decreases. So we want to show the difference between the two numbers in our bags, right? The number of balls strictly decreases every time we make a move of this algorithm. So how do we do that? Okay, let's track what we're actually doing here. We're going to use arbitrary variables, A and B, right? To make this a very general argument to show it always works. So let's start with our two numbers. Instead of 90 and 37, we're gonna have A and B, where let's say A is bigger than B, right? Okay. um, so our current right, our current difference is clearly just A minus B. That's the difference between the two numbers. I mean, that's kind of like the definition, right? We get the bigger number, we subtract the smaller number, and that's the difference, right? Okay, let's apply a move from our algorithm. So, like I said, our first step that we chose was subtracting subtracting a number such that the smaller one becomes 1. In this case, that number is B minus 1 because, B minus 1 will make the smaller number go to 1. And then the bigger number will be a minus b minus 1, which is a minus b plus 1. Great. So now we have our next step of the algorithm, which is we're going to multiply by 2 to the power of k, right? Okay, so what is this k that we're multiplying by? Remember, we're only multiplying by 2 up until the point where, up until the first time that we get bigger than the other number. In other words, 2 to the power of k is the smallest power of 2 that is bigger than a minus b plus 1. So if I try to, you know, like notate that on the side, we have that a minus b plus 1 must be bigger than 2 to the k minus 1, right? That's the smaller power of 2. And it is less than or equal to 2 to the power of k, because 2 to the power of k is the first power of 2 that is larger than or equal to a minus b plus 1, right? So that's an inequality that kind of like contains the information that we want. Okay, so we just applied a move of our algorithm, right? We made it we reduced the smaller number to 1, and then we multiply it by power of 2. And what we want to do is we want to show that after applying one move of this algorithm, the difference has strictly decreased. So remember our original difference, right? Sorry, instead of saying current difference, I should maybe change this to original difference, right? The difference we started with before we applied a step of our algorithm is a minus b. And our new difference, right, is, well, we know that 2 to the k is larger than or equal to a minus b minus 1. So we'll put that number in front. Well, okay, it's 2 to the k minus a minus b plus 1, right? That's the difference. So what do we need to show? In order to show this algorithm works, we need to show that the original difference is larger than the new difference, right? So we want to show, right? Okay, want to show that original difference is larger than the new difference. Okay, but we have expressions for the original difference and the new difference, right? So actually, if we rewrite this in terms of our variables, we have a minus b, which is our original difference, is larger than 2 to the k minus a minus b plus 1. Oh, sorry. This one should be a minus 1. Wait. Well, it should be inside the bracket, right? A minus b plus 1. Right? Okay, let's rearrange this a little bit. If we rearrange this a little bit, we see that um this is the same as, okay, I guess we can take this out as a minus 1 at the end. Let's move this over here, right? We'll move this a minus b to the other side. So if and only if 2 times a minus b is bigger than 2 to the k minus 1, if and only if a minus b, here we're dividing by 2, right? If and only if a minus b is bigger than 2 to the k minus 1 minus a half, where we just divided the entire thing by 2. So we want a minus b to be bigger than 2 to the k minus 1 minus a half. But, right, actually, Um, if we add 1 to both sides, because remember we have a minus b plus 1 here. So if we add 1 to both sides, we want a minus b to be bigger than 2 to, so a minus b plus 1 to be bigger than 2 to the k minus 1 plus 1 half. But we know, right? We know that, like we know that a minus b plus 1 is bigger than 2 to the k minus 1, right? From this inequality up here. But remember that these are integers. So when we have something that's bigger, we can actually make it a bigger than or equal to, well, 2 to the k minus 1 plus 1, right? Because these are integers. So to be bigger than 1, you must be at least 1 more than it. Okay, great. So if it's bigger than or equal to 2 to the k minus 1 plus 1, it is certainly bigger than 2 to the k minus 1 plus a half. So this is true. Therefore, all this entire chain of inequalities is true. Therefore, this inequality, the original difference is bigger than the new difference, is also true. So we've shown that no matter what two numbers we start with, if we do this move where we reduce the smaller one to 1, then we multiply it by a power of 2 such that it becomes bigger than this other number, the difference between them strictly decreases. Notice it's strict, right? And as you apply this algorithm more and more times, make more and more moves, the difference decreases more and more. Since the difference is originally some positive integer, which is finite, and it decreases by at least 1 every time, it must eventually end up being 0. And once it's 0, you have the same number of balls in both bags. You can obviously just minus that number of balls from both bags and end up with the no balls in either bag. So that's that part done. And the next part is it now always possible to empty both bags if we replace this doubling operation with a tripling operation? Okay, and maybe like like because they've already asked the question where you just provide an algorithm, you might be inclined to believe that the answer is no, you cannot, right? Because like it feels right that they would ask, like it feels right that that this second question is like different from the first question, right? Um, like they wouldn't just ask you the same thing twice. I mean, maybe they would, right? But it seems more likely that the answer now is no, and that is true. So you can try with some simple cases. Um, and a lot of the times, yeah, it's not gonna work. So maybe if we just start with like, the simplest non-obvious example, 1 and a 2. Um, like the example with one bag having 1 ball, one bag having 2 balls. Or already this example doesn't work. Sorry. And in this case, we're not looking at a monovariant. In this case, we are looking at a invariant. Invariant. So something that doesn't change, um, which like gives us reason as to why we'll never be able to remove all balls from both bags. Um, so like we're trying to notice something that kind of stays constant throughout this um throughout this procedure. Okay, let's you know we can try like do what we were doing before, but it's really not gonna work. I mean, like we can try a lot of stuff. Maybe I'll try multiplying this number by 3 now. And maybe I'll multiply them both by 3. Whatever. Then maybe I'll subtract 1 from both sides. Maybe I'll try multiplying this side by 3. Hey, look, we're kind of close, right? 6 and 5. Like, I like where this is going. Um, but there's really no way to proceed from here. I mean, maybe we can try multiplying, minusing 3 from both sides, I guess. I don't really know. But yeah, I mean, if we do this, look, we're just back at we're back at 3 and 6, which is where which is like right here, yeah. So okay, it feels like we're going around in circles, and if you try doing this a bunch of times, yeah, it's never gonna work. Okay, why is this? And the reason is because actually, if you look at the two numbers, I mean, this is a pretty common thing to look for in invariance, right? Maybe something you can try is looking at a mod 3 because we're multiplying by 3, but that doesn't necessarily work. So then, I mean, like one of the first things you should look for is just consider parity, right? The oddness or evenness of the numbers. So notice that we start with one odd number and one even number. And hey, look, this is an odd number, this is an even number. Odd number, even, oh, sorry, even number, odd number, even number, odd, even, odd. Okay, it looks like there's always going to be one odd number and one even number, given that we start with an odd number and an even number. Why is this? Well, okay, this multiplying by 3 operation, an odd number will remain an odd number afterwards, right? And an even number will remain an even number after you multiply by 3. So multiplying by 3 doesn't change the parity of numbers. And subtracting the same number from both will keep an odd number and an even number. Again, still an odd number and even number, right? Because you're changing the parities together at the same time, right? So if the parities are different at the start, odd and even, they're always going to be different. It's always going to have one odd number and one even number, which in particular means they're never going to be the same number because that would mean their parities are the same. Therefore, um, yeah, cool. We're never going to be able to get an odd number and even number. Um, okay. So yeah, the answer is no for part 2. And I guess maybe we have time for one more problem. Where by time, I mean I'm just gonna present the solution. And if you're like I genuinely, I'm not confident there's anyone actually listening to me right now. So if I guess if you're watching the recording sometime in the future, I won't give you guys time in the video, but you can just pause it or something and you can try this problem yourself. Um, okay, let me find a nice problem. Oh wait. Hmm. Ah, okay. Problem 4 here is kind of nice, and yeah, okay. Let's have a look at problem 4 on 2015. Okay. James has a red jar, a blue jar, and a pile of 100 pebbles. Initially, both jars are empty. A move consists of moving a pebble from the pile into one of the jars, or returning a pebble from one of the jars to the pile. The number of pebbles in the red and blue jars determine the state of the game. The following conditions must be satisfied. The red jar may never contain fewer pebbles in the blue jar. The game may never be returned to a previous state. What is the maximum number of moves that James can make? And okay, so I'll give you guys a bit of time to try the problem yourself. Um, you can pause it here. Oh, wait, why am I on YouTube now? Okay, you can pause here if you want to try it for yourself, right? And if you want a hint, I guess the hint is consider what we were doing before with the first problem, where you actually visualize it as a grid. That's quite useful for this problem. Okay, cool. So I'll just draw up the grid that we need now. Um, Maybe on one side we'll have, I guess on the bottom I'll have number of pebbles in red jar, right? Um, and on the right, on the left, sorry, right, number of pebbles in the blue jar. Okay, so um, oh yeah, we can kind of visualize this. Well, if I draw on a grid, right? Um, Maybe I'll hmm. Okay. Um, I just want to make sure um I'm doing this correctly. I'll just again I'll quickly change the question, I guess, a little bit. Because I'm not gonna drop such a huge grid. I'll change the pile of pebbles to only 10 pebbles. Yeah. I'll change it to 10 pebbles again. Okay. So we have I'm gonna draw a 10 by 10 grid, right? Oh God. It really should be an 11 by 11 grid because we're gonna have 0 pebbles as well. But 'So each of these cells represents one possible game state. So this is 0 pebbles, 1 pebble, 2 pebble, 3 pebble, 4 pebble, 5 pebble, 6 pebbles, 7 pebbles, 8 pebbles, 9 pebbles, 10 pebbles. Right? 0 pebbles, 1 pebbles, 2 pebble, 3, 5, 4, 4, 6, 5, 6, 7, 8. So on you start on this cell, right? Because both the initial game state is that both pebbles have you know no have zeros pebbles in it. And what you can do, there's two moves you can do. You can move a pebble from the pile into one of the jars. Okay, that's kind of like just increasing the number of pebbles in one of the jars, right? Something like this. And the other move is moving a pebble from the sorry, returning a pebble from one of the jars to the pile. Okay, well that's like going backwards, right? So you can kind of basically what that corresponds to is you can kind of like move laterally in any direction um on this grid. But there's a few restrictions, right? There's a few restrictions. The first restriction is that there are only 100 pebbles. Well, in our case, there's only 10 pebbles. What that means is that um, there are some borders which I'll draw in blue. Okay, there's some borders. So you can never like this square is unattainable because that would mean 11 pebbles in total, 10 and 1, right? Similarly, like all of these squares where the total number of pebble counts is more than 10, these are all like off limits. So I'm going to draw like a hard border along the staircase, right? Everything outside of this outside of the staircase is not attainable. Like this is not no good. You'll never be able to reach that. The second restriction is you can't return to a previous state. I mean, you can kind of tell that this the problem is kind of contrived in a way such that it's meant to be solved using a board like this, right? Because that condition is basically just saying you can't double back on yourself in the path. You have like the path can't ever return to a cell you've already visited before. So, like a path might look something like this, right? But finally, you have the final condition, which states that the number of pebbles in the red jar may never be fewer than the number in the blue jar. Okay, so what options does that eliminate? Well, this option will be eliminated because that means that the red jar has 0 while the blue jar has 1, right? Similarly, this one, this one, this one, this one. Okay, all of these are kind of eliminated, right? Right. The number of pebbles in the red jar must be greater than or equal to the number of pebbles in the blue jar. So now we have our restricted board, and basically this is kind of like the entire problem, right? It's like how many moves can he make? Like at most, how long can this path be? And you can kind of see that you can't reach every cell in this, right? Because like clearly, if I go into this corner, I'm kind of trapped, right? And I'll never be able to go back out because I can't retrace my steps or go to a cell I've already been to. So you're not going to be able to cover every cell. But the question is, how many cells can you cover? Or how many moves can you make? Um, and okay, time's running out. I'll just quickly say uh coloring, right, is my hint. Whenever you have something like this, where you have a kind of like a jaggedy board where you're trying to like do some number of moves in it, where you're moving from cell to cell. I mean, chessboard coloring is always good to try. So if we color this with a chessboard coloring, um, you know, right, like alternating black and white across the diagonals like this, we'll see that every time you make a move, right, when you go from cell to cell, you always move from a black cell to a white cell, or from a white cell to a black cell, right? You switch the color of your cell every time you move. For example, I start with a black cell, I start on a black cell, but then I go white, black, white, black, white, black, white, black, white, black. Let's count how many black cells and how many white cells we have. Black cells, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And white cells, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Since we start on a black cell and we alternate black, white, black, white, black, white every time, after we visit all 15 white cells, we would have only visited 16 black cells, which means that we miss out on 6. So like at best we can visit 16 black cells and 15 white cells, right? Which is something like this, right? Like this is an example of a path which is like quote unquote optimal. Notice that we miss out on 1, 2, 3, 4, 5 black cells. So like optimal path is 16 black cells, 15 white cells. You visit 31 cells in total, which is equivalent to making 30 moves. So for our simplified example of 10 here, we have the maximum number of moves James can make is 30. But if you scale it up to 100, I don't know. You can calculate that yourself, right? You can count the number of black cells and white cells using like triangular numbers and stuff, right? Notice that there's 7 black cells here, then 6, then 5, then oh sorry, wait, 2, 3. Sorry, 6 and 5, then 4, then 3, then 2, then 1. So B is the 6th triangular number, W is the 5th triangular number. Like I guess for the 100 by 100 case, black would be the 51st triangular number, and then number of white cells will be the 50th triangular number. And then you can do the same like kind of analysis and figure out the actual answer. So okay, maybe that'll be a bit of homework for you guys. Cool. So I think that's time. Right.